Hi, good morning everyone. We're going to be talking about some examples of physics applied to the superhero world. So oftentimes we see these crazy examples of runs, jumps, leaps, things that just wouldn't happen in our world. And what I found actually when I was breaking down some of these examples is a lot of times the physics actually isn't so bizarre. You'll see today as I go through these examples, a lot of them don't work and they do start to fall apart, but as we go through, a lot of times the physics does work. So let's get started with Thor, particularly Thor's hammer, Mjolnir. So according to Stan Lee, Thor flies with something he calls hammer propulsion. And essentially, hammer propulsion equals conservation of momentum. Now, conservation of momentum is essentially any object with mass gains momentum as it moves. Now, this value is simply the product of mass and velocity. Likewise, when an object with mass moves around some axes, it gains angular momentum. But both kinds of momentum are conserved. You don't create or destroy momentum, you just transfer it from one place to another. So, applying this to when Thor is attempting to fly with his hammer, if he's swinging it around, so the mass of the hammer times the velocity of the hammer equals the mass of the hammer plus the mass of Thor times the velocity of Thor plus his hammer. We can see that in the equation form here. So the mass of Mjolnir is sometimes assumed to be infinite. For purposes of the calculation, we're going to attach a very large number to it. It was once stated that Mjolnir is made of neutron star matter, and that, implied by legend, it would weigh the equivalent of 300 billion elephants. So, assuming a single elephant weighs approximately 2,268 kilograms, that was, according to Wikipedia, that's an African elephant. So therefore, 200, so multiplying that out, we end up with 6.8 times 10 to the 14 kilograms. Now that is an insanely large number. So we'll also assume the following variables. So the velocity of the hammer, if we can assume Thor can throw at a pretty reasonably fast speed, so 45 meters per second, which is the speed of a major league pitcher can throw. And according to the Marvel Wiki, the weight of Thor is 291 kilograms. That's really heavy, by the way. It's like 600 and something pounds. So putting all of this together into an equation, so the velocity of the hammer, the mass of the hammer times the velocity of the hammer, and then we have, again, when Thor grabs onto the hammer here, we have the mass of the hammer again, plus the mass of Thor. We can solve for the velocity of Thor plus the hammer as he's flying. So once we isolate out that velocity, we end up with the same velocity as the hammer by itself, which is 45 meters per second. So the speed that Thor releases the hammer is also the speed at which Thor and the hammer will travel. And it seems like an odd conclusion, but since the hammer is so heavy, a small addition to its mass won't slow it down at all. Now where this physics problem breaks down, and this wouldn't actually work, so please don't try this at home, is that if this were to happen, Thor wouldn't actually have any arms, because the force at which this were applied would tear his arms from his sockets. So our next example is Daredevil. So for anyone that's familiar with Matt Murdock, also known as Daredevil, he's blinded by a radioactive substance as a child. So while he can no longer see, the radioactive exposure heightens his remaining senses beyond normal human abilities, giving him superhuman hearing that allows him to navigate via a radar-like sense. So an example of Daredevil using this ability was shown in episode 5 of season 2 of the Netflix Daredevil series. And I'm not going to spoil this for anyone that hasn't seen Daredevil at all, other than I'm going to break down a small example. I do recommend you watch it though, because it's one of my favorite TV shows. But in this scene, Daredevil's trying to listen in on a conversation between one character, Elektra, and a group of his executives. So he climbs to a rooftop of an adjacent building, and he's clearly shown listening in on the conversation taking place. I'll remind you, this is within another room that's in another building across the street. Now that's pretty impressive. And as he indicates later in the episode, he hears the entire conversation. So how sensitive must his hearing actually be? So to get started, I want to break down some of the basics of sound. So sound is simply energy that creates vibrations within a particular medium. So when sound is produced, it moves the particles of the medium. They bump into the next particles, and the original particle oscillates back and forth. So frequency is a measurement of waves per second and is measured in hertz. So 100 hertz equates to 100 waves per second. Therefore, if we have 8.4 kilohertz, that is equal to 8.4 times 1,000 waves per second, and we have 8,400 waves per second. So sound is created by moving something, or something moving something, and moving something requires an application of force. The rate at which that force is applied is what physics calls power, and this is measured in watts. So generally, sound moves away from source in a sphere. And the rate at which energy of the sound flows through the sphere of expanding sound is called intensity. And this is measured by dividing the watts by the area of the sphere. Now the equation for this, and the reason I'm going over this is because we'll use this later on when we solve for a problem, is I, or intensity, equals watts divided by meters squared. Now, relative intensity of a sound is called the intensity level, or the decibel level. The volume of sound, measured in decibels, decreases proportionally to the square of the distance the receiver is from the source of the sound. Now, for a reference, a normal level of conversation in a room is roughly 60 decibels. So for two people talking to each other, that's what we would expect. It's also important to remember that decibels are measured logarithmically. That means for every 10 decibel decrease, the volume is roughly cut in half. Now, to get to our problem solving, we're going to make one major assumption in these calculations. So with Daredevil being on the top of one building and Elektra and the executives being inside a room in the other building, there are a lot of windows, walls, city noises, etc. So to make the physics a little easier here, we're going to strip that away and assume that there's no external noises and no windows and walls between them. there is a clear line of sight, and during this scene, Daredevil can see Elektra and the people that she's talking with. So the first step here is we want to solve for the intensity of sound. So since sound emanates in a sphere, the energy is equal at all parts on the surface of that sphere. You almost want to imagine kind of a bubble originating at the source and emanating out from the people that are talking. And if we can calculate the sound at any given point on that sphere, then that's how we can visualize what's happening here. So therefore, if we can think of Elektra sitting 2 meters from the speaker, then she's at the edge of the sphere that is receiving so many watts per square meter. So at 2 meters, we need to go back to thinking about decibels at intensity level. And that's our equation here. So beta is our decibels. Intensity is what corresponds to the decibel value. Intensity at 0 is the reference intensity, and that is sound intensity at the threshold of human hearing. That's a given value, so that's something that we can just plug in. And we can solve for our equation. So here we have 1 times 10 to the power of 6 watts per meter squared. We're going to hold on to this value, and we'll use it later on as we solve through our problem. So as we discussed earlier, the definition of intensity of a wave's energy is power per area. And at this point, we know the intensity. We know the distance Elektra is from the source. We've said that she's 2 meters. We also know that sound emanates as a sphere. Therefore, our equation is I equals P for power over 4 times pi r squared. So if we plug our values in, so using the same calculation that we figured out earlier, we're going to solve for our P. We end up with 5.03 times 10 to the negative 5. Now that's the power used by the speaker to produce a 60 decibel sound at 2 meters. And that's what Elektra hears. Now we can move on to calculate the intensity of sound at Daredevil's position. For this, we simply just use the last formula, but this time we use a new value for R and solve for the intensity. So our R value, Matt Murdock or Daredevil, position is at 42 meters. That's because he's 40 meters from Elektra, who is 2 meters from the source of the sound. Again, remember our sphere, our bubble that is radiating out. Our P value is power. That hasn't changed. The power that the speaker is using is still the same. Our R value is now 42 because that's the distance. And at this point, we're solving for intensity. So now we have 2.2 times 10 to the power of negative 9 watts per meter squared. From this, we know the intensity at Murdock's location, so we just need to use our first formula so we can figure out the decibels at Daredevil's position. So using our known value, we can sub that in here. This is a given constant here. Solve through the equation, and we have 34 decibels. Now, that doesn't seem like much of a difference from a 60 decibel level of a normal conversation within a room, but we're working with a logarithmic scale. The volume of a whispered conversation is 30 decibels, and Daredevil hears it just fine outside the room on top of another building. The other consideration is that we assumed no walls, no windows, or other city noises in our calculations, and those would have a significant decrease in impact on the sound intensity that Daredevil hears. So our next example is Spider-Man. Now, in my opinion, Spider-Man is a physics expert. His masterful web weaving is one extremely complex differential equation that he essentially solves in real time. But you don't need to be an engineer or a physics expert yourself to understand his smooth moves. You just need to have a sense of how pendulums work as he swings between buildings. So let's start with his web swinging. So once Spider-Man starts swinging, he becomes just like a pendulum. So his motion is determined by the length of the web along with its starting angle. So from a forces view, there's mostly just the tension in the web and the gravitational force pulling down on him. So there's a scene in one of the movies when Peter Parker is quizzed by his science teacher on the formula for angular acceleration of pendulum. Peter's answer of angular acceleration equals gravity times sine of theta is both correct and also a reference to Spider-Man's pendulum-like transport. Now for his web shooting, if we assume that Spider-Man's web acts like an unpowered projectile, so like a bullet rather than a rocket, we can calculate the initial shooting velocity required to reach the tops of buildings with his shots. So first, let's try ignoring air resistance to keep things simple. We'll need the acceleration due to gravity and the height of the shot. So if we look at velocity, square root 2 times gravity times the height. So if we assume, let's say 100 meters, so that would be a building of 30 to 40 stories. So we're looking at pretty tall buildings within a city, gravity being 9.81 meters per second squared. We end up with a velocity of 44.29 meters per second. Now that's not overly fast. For reference, a bullet from a .22 rifle exits the gun at a speed of about 300 meters per second. Now his web strength, most people have heard common sayings about spiderweb being stronger than steel, but that's generally a myth. On screen it looks like Spider-Man swings on a pretty thin bundle of web. Now, is this realistic, assuming that his web is like a normal spider's web and not some magical Marvel technology? Now, spiderweb has a tensile strength of about 1,000 megapascals. This means it can support 109 newtons per square meter. 1 billion newtons is the force required to hold 100,000 ton weight. Now the square meter refers to the cross-sectional area of the web. So if the strand is a cylinder of width 3 millimeters, then we can calculate the area. So area is equal to pi times r squared. So our radius here, assuming the width of 3 millimeters, is 1.5. We end up with an area of 7.06 millimeters squared. That means that the web strand can hold a static force, V times area times tensile strength, which, as we discussed, is 1,000 megapascals, is 7,068 megapascals. So the units end up working out to be 7,000 newtons. My unit's got a little screwy here, but what it works out to be is a static force of 7,000 newtons. So what that equates to is that the web strand can support a static weight of about 720 kilograms. Now, assuming Spider-Man, he's a pretty small guy, assuming he weighs, I don't know, 70, 80 kilograms, he has a lot of room to play with. So if he is using his web to catch other people or whatever else, he also has his web to rely on when he jumps off buildings, when he falls. As he exerts a dynamic load on the web, his effective weight increases by several times. But 720 kilograms is quite a lot to rely on. So our last example for the day is the Flash. So the fastest thing that we know of is light, and the Flash has been known to outrun it. So if we look at our equation here, time equals distance over speed. What I'm working out here is that if light travels at 186,282.397 miles per second, and the circumference of the Earth is 24,902 miles, then it would take 1 second, if we multiply it out by 60, we could go around the Earth essentially in 0.13 seconds. So if we were to travel at the speed of light, we'd be able to go around the world 8 times in 1 second if we were the Flash. Now, humans are nowhere near close to running at light speed, but hypothetically, if I were able to run at light speed, what would happen? So, firstly, when we run, we use energy. So, calories are a measurement of energy in food. So, when we use energy, we burn calories. The faster we run, the more energy we use, and the more calories are burned. So an average person burns generally 100 calories per mile. Assuming we were traveling the full circumference of the Earth at light speed 8 times over, we would burn, this would increase dramatically, but it's an estimate, we would burn approximately 1.99 times 10 to the 7. So 10 million calories. Now, the typical adult takes a year to burn about 1 million calories. By normal human standards, the Flash just expended 10 million calories all within 1 second. Now, if that's not some crazy physics going on, then I don't know.